All right. Hey everybody, we are going to be doing the pre-lab for the toxic waste cleanup lab. So what I would like you to do before you go any further is please make sure that you have read the introduction. If you haven't, please pause the video right now and read the introduction. So there's several pre-lab questions that you need to be answering as we do this, and there is the last one, which is actually doing some calculations and perhaps doing some stoichiometry stuff that you haven't done since a chemistry class. So basically, human beings have an idea, or actually societies have an idea, that the solution to pollution is dilution. And you can see that what we tend to do is we tend to take our waste products and dump them in the nearest available body of water, whether it's a river, whether it's a lake, or whether it's an ocean, and it will get diluted to a level that is safe. Or we pump it into the air, and the same thing happens there, is that the toxic waste tends to disperse and become dilute to a level that is a little bit safer. Look at all those smokestacks in that picture. That is just a small, actually that's just a small sample of a much larger area that has even more smokestacks in it. I think it's Calumet, Michigan, back around the turn of the 1800s to the 1900s. And there are a lot of copper mines up in that area. And that leads me into this. Torch Lake in Michigan is a site of a Superfund cleanup. And just in terms of mining waste, we've talked a little bit about mining waste. We've done labs with that. Torch Lake is a Superfund cleanup site. Amongst other things, the lake still has, after the last copper mining tailings were dumped in the lake in the 1930s, there's still 3,800 parts per million of copper metal that's dissolved in the lake. And actually that the machine that you see in the front is a reclamation project that the mines were actually using. So the lake was used to dump tailings from the processing of the copper. And these tailings still had so much copper that in the 1950s it was figured out that, hey, we can go into the lake, pick up these tailings, and still produce profitable copper. And in 1968, that machine right there, it broke during a really severe winter, and it's just been sitting in the lake since 1968, which is kind of an interesting thing. But anyways, so there's copper that needs to be cleaned up in this lake, and there's remediation projects happening even right now. So we're in the lab, we're going to use a colorimeter, and this is an instrument that is going to be looking at light shining through some various amounts of copper chloride solution. And the amount of light that gets absorbed will tell you how strong the solution is. And when we get our data, we're going to be looking at the concentration of the solution and the absorbance of the light. And we're going to be looking to develop a curve. And the curve, I think in this case, is going to be a straight line. It should be a linear regression will allow us to figure out what the relationship is between the concentration and the absorption. So basically, we're going to get a line graph. And these are the samples that I'll be measuring a little bit later. And you can see on the far left is on the far left, that's our 50,000 part per million solution of the copper chloride solution. And what you need to do right now is have a look at that data table on the first page. This is our serial dilution. And each one of those has a slightly different concentration to it. And what you should do right now is determine what the dilution factor is. And it looks like if we are using 50 5 milliliters of the 50,000 part per million solution and 5 milliliters of distilled water to make 10 milliliters of new solution, it looks to me like in each case, then that's going to be the pattern, that we use 5 milliliters of the previous dilution and 5 milliliters of distilled water. It looks to me like we've got a 50% dilution each time, so please, at this point, calculate out the concentrations of each of those dilutions before we go any farther. Okay, so now you've calculated the dilution of each one of those test tubes, 1 through 7. And now this is what we're going to wind up with. We're going to wind up with an absorbance versus concentration graph. And from that, we're going to be trying to determine in part 2 whether we have cleaned up the copper chloride solution sufficiently. And so we're going to get a new absorbance level from the remediated copper and whatever that absorbance is. So let's just say that the new absorbance will be, and this is not our data by the way, let's say that the new absorbance is here at 0.12. We'll read over, and that's going to get us a concentration of about 1 part per million. So we'll use the line itself to determine what the concentration is. Now before that, you are going to be making a prediction. Actually, you're going to be making 2 predictions. You're going to use your chemistry skills here. And this is on the 3rd page. It's under the 2020 COVID alternative procedure, some stoichiometry calculations. So what I want you to do, and this is going to be kind of difficult. It took me about 2 tries to figure out the right way to make this calculation. So you're going to have 0.052 grams of aluminum that's going to be reacting with the copper chloride. Now, if you look right here, this is the reaction that happens. It's a simple single replacement reaction where we have the copper chloride, we react it with the aluminum, and you can see the ratios that we'll have 2 moles of aluminum will produce 3 moles of copper because those are the mole ratios. As a reminder, the coefficients of a balanced equation do show you the mole ratios. Now, we're going to start with 10 milliliters of a 50,000 part per million copper chloride solution. So you don't really know what the molarity is of that solution. That could be something that maybe you'll need to calculate. Some other information is this. 1 part per million, by definition, is 1 gram in a 1 million gram solution. Or if you think of it in terms of moles and liters, maybe, this isn't quite moles and liters, but it would be 0.001 gram in 1 liter of water. You'll also want to know that the atomic mass of copper is 63.55 grams per mole. The atomic mass of aluminum is 26.98 grams per mole. And the molar mass of copper chloride itself is 134.45 grams per mole. Now, one last thing I didn't talk about. So the main idea is you're going to determine the amount of copper replaced by the 0.052 grams of aluminum. But then after you have done that, the other thing that I want you to predict is what will be the absorbance. So after we get the concentration absorbance curve completed, predict what the absorbance of the experimental result will be after we react this 0.052 grams of aluminum with the 10 milliliters of copper chloride solution. Now, if you like a challenge, you're on your own right now, and you can start working on your calculations. If you want a little bit more guidance, the next page I'm going to give you some guidance, but I won't tell you exactly every detail, but instead it will give you the basic steps, and you'll have to use your chemistry skills to figure it out. So here's how you can figure this out. So first of all, you can use the grams of aluminum and your stoichiometry skills to determine the grams of copper which will react with the aluminum. And I'm really bothered by the fact that I don't have a capital C there for copper. So we'll get the grams of copper that should react when you have 0.052 grams of aluminum. I need to backtrack just for a second. Okay, it does say 0.052. Then, what you probably want to do next is determine how many grams of copper chloride are in the 10 milliliter solution. And you'll have to use the parts per million idea. You'll have to use this information right in here, that there's 0.01 grams. 1 part per million is 0.001 grams if you have 1 liter. But remember, we've only got 10 milliliters. Then, once you've determined the number of grams for the copper chloride in that solution, determine the grams of copper in the 10 milliliter solution. And to determine that, you might want to use this number right here, the atomic mass of copper, and you might want to use this number right in here, the molar mass of copper chloride. They could both be quite useful to determine how many grams of copper are in the 10 milliliter solution. Then I will let it out of the bag that not all of the copper that's in that solution will react. So determine the difference between the grams of copper in the solution and the grams of copper which will react. Then what you get to do is convert that mass of copper, that unreacted mass of copper, into parts per million of copper chloride. And then once you've figured out what the parts per million of copper chloride are, you've got the concentration, you can go back to this curve right here and then use the curve to go the opposite direction to figure out what the absorbance will be. So if you know what the concentration is in parts per million, read up to the curve and then determine the absorbance value. So there's a lot of challenge in this. I think it's really kind of a cool challenge. So good luck with this. And I will be giving you data on this lab probably, no, not probably, but I'll be giving it to you on Thursday, Thursday. All right, see you later and good luck with that.